So now that we understand a bit more about equilibrium, let's take a look at some specific types of problems involving equilibrium calculations, some things that can happen in these solutions that we're looking at. So this whole chapter is all about how do we apply the concepts of equilibrium to real type problems. To start with, we're going to talk about something called the common ion effect. So the common ion effect occurs when you have a substance that's already contains an ion that's part of your equilibrium. So if you, for example, have an equilibrium situation and you add more of a particular ion, we know according to Le Chatelier's principle that's going to cause the equilibrium to shift. Using that information, and now what we can do with our calculations, we can figure out how is that going to affect the concentrations. Okay, so this is specifically important for polyprotic acids. Why is that? Why do you think that polyprotic acids specifically have this? Well, think about it. First dissociation creates H+. That H+, then, for the second dissociation, that H+ is already there. That affects the concentration, the initial concentration of the H+ for the second dissociation. Okay, so we've already sort of seen that. Here's an example using the common ion effect. So we have a solution of HF, and there's your Ka value for HF, and NaF. Okay, so we know that NaF dissociates to form Na+ and F-, and HF is at equilibrium with H+ and F-. So the common ion here is the fluoride ion, right? The major species in this mixture are going to be HF, sodium ion, fluoride ion, and H2O. The presence of that fluoride ion from the NaF is going to shift the equilibrium position of the HF more towards the left, right? We've added more F-, so more product, which means it's going to shift it back towards reactant, okay? So we have to consider that sodium fluoride breaks apart first to produce fluoride ions. Why is that? Well, because it's an ionic compound and it completely dissociates and it puts the ion into solution. Okay? And then that's going to cause the dissociation to shift backwards. So the H+ concentration of HF will be lower than it would be without the extra fluoride ion, which means if the H+ concentration is lower, then our pH is higher. So this will actually decrease the pH or increase the pH of the acid. Okay? What would happen to the pH if we use a mixture of NH4Cl, ammonium chloride, and ammonia? Now, ammonia is a base. It's a weak base. Ammonium chloride is an ionic compound. Okay? So NH4Cl splits into NH4+ and Cl-. NH3 can accept a proton from water to become NH4+ and hydroxide. While the common ion here is clearly the ammonium ion, so that's going to have an effect. Okay? If I have a solution that contains more ammonium ion than it should, it's going to shift the equilibrium of the NH3 protonation back to the left. That's going to lower the hydroxide ion concentration. If it lowers the hydroxide ion concentration, it's increasing the H+ concentration, which therefore lowers the pH. Okay, so this is qualitatively looking at how the common ion effect works. Now, here I have the concentration of hydrogen ions at equilibrium is 2.7 times 10 to the minus 2 molar. And the percent dissociation is 2.7% for this concentration, a 1 molar concentration of HF. Okay, I want to know what happens if I put this same 1 molar HF into a solution that contains already 1 molar sodium fluoride. Okay, that's what I want to do, is figure out what happens to the H+ concentration if I do that. How does the common ion, fluoride ion, affect the concentration? We already know qualitatively what it's going to do, right? We already know it's going to shift the equilibrium of HF back to the left. It's going to lower the H+ concentration and raise the pH, but we want to figure out by how much. Okay, so our major species are going to be HF, Na+, F-, and H2O. The HF equilibrium expression is HF is in equilibrium with H+ and F-. Okay, so let's set up our ICE table. HF, the initial concentration of HF is 1.0. Now normally we'd write 0 and 0 on the left side of this reaction, but we already have 1 molar of fluoride ions there. So the initial concentration of F- is now 1 molar. The change, it's one-to-one-to-one stoichiometry, so the change, the concentration of HF is going to go down by some amount x, which means the concentration of H plus will go up by some amount x, and so will fluoride. It'll go up by some amount x. When I add them together, I get 1.0 minus x, x, and 1.0 plus x. I put that into my expression for Ka, which is the concentration of H plus times concentration F minus over concentration of HF. I make the approximation. I'm assuming that because my Ka value is times 10 to the minus 4, that x is going to be very, very small. And then I can make the approximation. And what I end up with is that x is equal to 7.2 times 10 to the minus 4. Okay? If that's the case, that's the concentration of H plus at equilibrium. That means my pH is 3.14. Percent dissociation is the amount dissociated, in this case x, the amount of H plus produced, over the initial concentration of the acid, which is 1 molar, times 100. So I have 0.072% dissociated. So look at the difference between when I didn't have any NaF in there and when I do. It used to be 2.7%, it's now down 0.072%. So the fluoride ion that was in there to begin with, the fluoride ion from the NaF, really affects the equilibrium position here.